Okay, so in this lesson, we are going to learn about Bernoulli trials and Bernoulli distribution. A Bernoulli random variable is going to be a random variable which can take only two possible values. Usually we call it as 0 or 1. So let's go to the slide. So here you can see Bernoulli trials. Each trial results in one of two possible outcomes. We usually denote as success or failure, so which is going to be 1 or 0. Okay, um, so the support of the random variable is going to be 0, 1. Basically, the image of random variable. Remember, it's a function. Okay, so it can take 0, 1. So 0 usually denoted as failure, and 1 is success. Now, Bernoulli trials you will see in real life a lot. For example, if you take an exam, then the possible outcomes are either pass or fail. If you toss a coin, then possible outcomes are either head or tail. If you do a clinical trial, either it's a success or failure. So Bernoulli random variable can be seen in real life many times. So now we have the probability of success we denote as P, and the failure Q or 1 minus P. So if I draw the probability distribution table, I would have something like this. So X can be 1, let's say success, okay. It's going to be P, and then 0, which is complement of that, 1 minus P. Remember that when you add this, it's going to be 1. Okay, sum of probability. That's going to be 1. Another thing about this Bernoulli trial, trials are independent. That's really needed when we go to the binomial distribution. In Bernoulli trials, you have only one single trial. So this statement may be therefore to develop binomial distribution. So now we want to talk about the probability mass function. So what's the probability mass function? So one way you can write it as like this. You can say probability x equal x. You can divide by case. It's either 1 minus p if x equals 0 or p if x equal 1. Okay. The same thing from this table. I just wrote it as mathematical formula. Or you can write it as one line. This is basically px 1 minus p is 1 minus x, where x is going to be 0, 1. Okay. You can use one of these setup. So this is probability mass function. Okay. Once you have that, you can calculate the mean and variance, which is going to be very simple. So if you want to calculate mean, one thing about mean, you can use traditional. Let me introduce something new, something called the moment generated function. Moment generating function. The name implies what it's going to do. You can come up, you can generate, or you can get moments from this function. The definition of moment generated function is going to be expected value of e to the tx. Okay. So here is t, here is t, then this is random variable. That's the random variable. So if I try to, why we do this? Once you have moment generated function, and if you take the k derivative, and then evaluate at 0, then you get the kth row moment. Okay. So that's why we want to do this. Okay, so this is very useful. So let's try to calculate the moment generated function for the Bernoulli distribution. So if I write this, x the value of x, which is going to be what? If I write this, I mean, as the definition, use the definition. This is going to be e to the tx time probability x equal x. So if I expand this, x can be 0, then probability x equals 0, plus x can be 1. Okay. So this one is going to be e to the 0 is 1, so this is going to be just 1 minus p, okay, because this one is 1 minus p, and this one is e to the t time, and then this is just p. Okay. So if I write this, rearrange it, that would be the moment generating function. Now, if I take the first derivative, so what's going to be? It's going to be p et and evaluate at 0. So that's going to be p. So this is the first moment. By the way, you can see that it doesn't matter which derivative you take; it's always going to be p time e to the power t. Okay, so if I take the kth moment for this particular distribution, it's always going to be this. So then the kth moment always going to be end up as p, because when you evaluate at 0, it's going to be that. So from there you can see that I can get the variance. Okay, so any moment is basically p. So it's going to be p minus p square, which is going to be p times 1 minus p. Okay. So that is the variance. So expected value is p, variance is p times 1 minus p. You can calculate any other moment using this moment generating function approach. So here the question asks calculate the expected value and variance. If you don't like moment generating function, you can go through the other second approach. So what's the second approach? You know the random variable x. Bernoulli, it can be 0 or 1. Probability for that is 1 minus p and p. Then the ex without using moment generating function is 0 times 1 minus p plus 1 time p. So end up as p. The second moment, 0 square and 1 minus p plus 1 square time p is p. Then you use the same approach in here to get the variance, p times 1 minus p. So ex is p, variance is p times 1 minus p. Okay. Sometimes you will see that as p times q, where q is basically 1 minus p. Some textbook use that notation, q to denote 1 minus p. So here you can see a question where stock price of company XYZ will be either 40 or 65. So instead of 0, 1, now we have two values. It can be either 40 or 65. So the probability is, I think, 50%. So 0.5, 0.5. So in this case, when you get the expected value, you just multiply these two, 40 times 0.5, 65 times 0.5, and then you add, and then that will give you the expected value. In 1 year, okay, not today. If you want to today price, you have to discount it. Okay, so basically 1/2 times 40 plus 65. Okay, so that's the end of Bernoulli distribution. And next one is binomial, which is extension of Bernoulli distribution.